We are the Light Rail Group. My name is Justin. This is Zach, Travis, Matt, Jason, and Rocco. And we are presenting the Light Rails. Next slide. Our project description is that we are looking at a macro scale design for the light rail system concerning Wasson Way and how that's going to involve the community and both tie into the I-71 line and the Oasis line. In our presentation today, we'll be covering 5 design options that we prepared. We cover geometric design and hub locations, transit schedule, and cost estimates. We then take all of that data and put it into a success criteria that we've developed, which helps us make our final recommendation. Moving forward, these are the specifics on the train that we are using for all our calculations. Moving forward.
Okay, so after we picked a composite train, the next step was actually developing the physical details for the single and double rail lines. So for our composite train, we had a 4.7 foot track gauge, so that was kind of the basis and the center lines of all of our drawings. Basically what we did for the single track is we offset the 2 edges of the rail lines by 4.65 feet on either side, and this gave us a 14 foot usable width for the single rail line. For the double rail, we did basically the same thing on the exteriors, but we scooted the 2 rail lines closer together, which gave us a 27.5 foot usable width, so slightly less than if we would have just doubled the single track. We also thought it was really important to include the bike path, even though we were mostly focused on the light rail line. So for the bike path, what we did is we offset the north usable width line of all the track options by 12 feet. And the intent was to use 10 of that feet for a bike trail, and the other 2 feet being an additional buffer. So now we can run through our 5 design options. So option 1 was the simplest. It's just a single track, which would have a single train that services all 4 stations. Even though it's a single train, you would have 3 composite cars per train, which would help it would increase the capacity. The primary advantage is that you would have a much lower construction cost in this option. Another huge advantage is it's a lot easier to implement the bicycle trail. There's a lot of areas where we only have a 30-foot right-of-way, so adding the bike trail to the 12-foot single track or 14-foot single track is a lot easier. Unfortunately, because we only have 1 car, your wait times are going to be a lot longer. Option 2 is the double track option. So here we just simply have 2 tracks servicing the entire Wasson line, and we have one train per track. This gave us a shorter wait time, but obviously it gave us a much higher construction cost. This is actually option 1 that we're showing here, but the reason we did this is the final 3 options are all using option 1 as a template, and then altering 1 or more things within that boxed section between Brookwood and Hyde Park Plaza. So for option 3, we simply added a passing siding to the Hyde Park Plaza station. The idea here is that we'd be able to run 2 trains on a single track so long as they pass each other at Hyde Park Station so they don't obviously collide. This would give us the low construction cost of the single rail line, and it would also make our maximum wait times a little bit shorter. Option 4 again worked off the single line template, but now we added a passing siding to Brookwood Commons as well. Again, the idea here was running 2 trains on a single line, but we just gave a secondary option for the trains to potentially pass each other. This led to even shorter wait times, but it increased the construction cost slightly. And then finally, option 5 is kind of a hybrid between the single rail and the double rail. So from Xavier Station to Brookwood Station, we'd have a single rail, and then that would diverge into a double rail line from Brookwood to Hyde Park, and then converge back to a single line from Hyde Park to Red Bank Station. The main advantage here is you'd have, again, a really short wait time, but of course you'd have a higher construction cost, and probably even worse is it makes it a lot more difficult to implement the bike trail, because that center section along Wasson Road is where we have our 30-foot right-of-way. Once we found our 5 design options, we modeled them in AutoCAD and then used those drawings for our construction estimate and also for our schedule.
So one of the items that we looked at for the design criteria for each one of the options was the maximum wait time. So the maximum wait time defined by us is, say you were at Brookwood Commons, and you want to travel east to Hyde Park Plaza, and you just missed the train that was heading east, how long are you going to have to wait for another train to leave your station heading east? So the maximum wait time is standalone, its own category in our success criteria, but the loop time of the trains also affected what the capacity and demand was of each of the train options and what the number of train crossings at intersections were. So we figured the best way to do this was to use the VISTA modeling software to develop a schedule, and then from that schedule we can find what the maximum wait time was between departures. But to ensure that the values we got from VISTA were correct, we also did hand calculations to ensure they were correct. So to do these hand calculations, we used kinematic equations and numbers from our component train. So we used an operational acceleration and deceleration, an operational max velocity, and then we assumed a dwell time of 30 seconds at each station. And then the dwell time is just the time that the train is stopped when it's dropping people off and picking people up to go on to the next station. From these equations and our component numbers, we were able to come up with acceleration and deceleration time of 11.66 seconds and acceleration and deceleration distance of about 300 feet. So all the things that are bold up there were also used in VISM, so we would have conformity between the software and the hand calculations. One other wild card that we had in these design options were in 3, 4, and 5, we had turnouts at the stations to allow the trains to pass each other and not collide. So you can kind of imagine the train entering there from the left. It would come in and it would have to either go straight or take the turnout. And if it took the turnout, it had to enter that entrance, which is called Frog, by trade name, and at 20 miles per hour instead of the 35 operational speed. So this added about 17 seconds to entering a station and then 17 more seconds when leaving. So a little over half a minute of additional time per turnout. So once we came up with all these parameters for each one of the designs, and we knew how long it took to get from station to station, we were able to calculate, if we took a train going from all the way on the east side, all the way on the west side, and send them towards each other, at what point they would collide. So this usually happened over by the Hyde Park Plaza station, just a little bit west of it. So, you can go to the next one. So to mitigate this, what we would do is keep the train stopped at the plaza that got there first, and allow the other train to first dock to the station before sending the other one out. So this increased the dwell time a little bit, but that's why we looked at all these design options, was to find which one of them had the smallest amount of increased dwell time. So from there, we can make the schedules and compare the departure times for either eastbound or westbound and find the maximum wait time.
Well, I was the VISM modeler for this project, so I spent most time running through VISM and getting the project stuff. Some advantages, I guess, of the calculations is it allows you to go along the same, travel line, the same distance as an actual train would. So it puts in the realistic things of turns and the speed up, slow downs you receive from hitting a turn and all that stuff. So you can add in more variables than easier than calculations. All the good things also, you can run multiple run times of reels, so you can run them over and over and over again. And also, it's ability to start the trains at different times. I know in the calculations, he had the train starting at the end at the exact same time. In my calculations, I'll show you in a few slides, it starts the trains at different times at a spread of 4 minutes. So either start 4 minutes ahead of the other one, or wait for 4 minutes and then it goes. So it gives you more of a realistic time of trains not always leaving the stations at the exact same time. Good night. And doing so causes some that you can see. This is the Brookwood. One of these trains pulls up, has to stop the train, waits its 30 seconds, it's accelerated, so pull faster. Waits its 30 seconds, pulls up here, has to wait for the train heading west to fly by. And now we can go again. So that's really what causes a really big variable in these times. Next one. Here's another one. This is option 5. So this is, I guess, the same spot, but the train has to come, stop, wait for the other one to come by, has to slow the other one by. And this causes variables in time. So obviously, if that train starts on the far right starts later, that train has to wait longer. So thus, its travel time is a longer distance. So using these, I set up a chart to find the best possible wait times and the worst possible times. And it gives me a big variable, and we use that for our final. So this gives a more realistic kind of feel of how long it's going to be. And also we found out that the fastest wait time is obviously the double track. The slowest was 1, the single track has only had 1 train. I think 4 and 5 were the fastest then, and then the third one was still faster than 1, but not as fast as 2.
Alright, so for our construction cost estimates, rather than starting from scratch, we started with the Oasis report, and we took all the unit costs from there, and then we just changed any items that we thought were going to be significantly different from that. So there's a short list of the items that we changed. I'm not going to go into details about any of them right now, but if you have any questions, I'd be happy to address them when we open it up for questions. So without further ado, here's construction costs for each of our 5 options. These were all basically right in line with like the $45 million per mile estimates that we've seen. And as you can see, options 3, 4, and 5 were very different because there was really not much difference between the options as far as track.
Go back just for a second. You said they're not much different from and then you gave us an estimated number, and I kind of missed it. You said something per mile?
Roughly $45 million per mile.
Okay, so how close are you to $45 million per mile?
The single track was basically dead on, and so was 3, 4, and 5. The double track was a little bit lower than 45 million per mile. I don't remember. And then for operation and maintenance costs, so the standard way that we found that most people would figure out operation costs is based on the revenue vehicle hours rather, per year, and then you just multiply that number by a constant multiple based on the type of vehicle. Since we didn't know what type of vehicle we were using, we used the average, which was given to us by the National Transit Database. We used the 2013 average for that. And then we also added another $175,000 per track mile for maintenance. And that's how we came up with our total operating and maintenance cost annually, as you can see there. Also, you can see it kind of makes sense. Our single track would have the lowest maintenance cost. And then option 2 would be the most expensive, with 3, 4, and 5, slightly less than those.
Okay, so throughout the remainder of this semester, we collected a lot of data, we did a lot of design. We had great results, but we needed a way to kind of compare them across the 5 design options. So we came up with a success criteria system that analyzed 7 different categories and kind of weighted them against each other to ultimately give us a recommended design option. So going around this pie chart here, the largest section was the construction cost. And that also included the earthwork that had to be done. So this is very important to us. We put 40 points out of the total 100 to construction cost, because if we can't get the budget passed for the initial project, the rest of this isn't going to be affected at all. Going around, the rest of these are weighted 10% or 10 points out of 100. We have operating costs, so once it's up and running, how much it's going to cost to keep it running, how much will employees cost to keep the train going throughout the year. Resiliency, if there's a train that breaks down on the track, will we be able to still serve our passengers and our riders throughout the day? And I'll go into that in a little bit more detail in the next slide. But community opposition, so that was based on the number of homes that we'd have to have an acquisition for in order to put in double track in certain narrow parcel areas. And also, how many times is a train going back and forth through the neighborhood? That's going to increase the noise and ultimately decrease the satisfaction of the neighbors that are surrounding that track. Maximum amount of wait time, we already talked about that. Safety, how many times, again, is a train going back and forth? That's more times it's going to be crossing over a roadway, more potential for a accident at an intersection. And we also considered the number of turnouts that were in each design. Turnouts have the opportunity for a derailment of a train. It's more likely to occur at a turnout than at a regular straight section. So we wanted to consider that as a safety factor. And then rider capacity, would the train or the option be able to support our 30-year demand? All right, next slide. So just one example of how we weighted this resiliency. We had the challenge that we wanted to quantify the ability of a design to recover from a train breakdown. So on the bottom here, the total track length is 4.1 miles. And what we did is we looked at what percentage of that track occurs between stations 1 and 2, stations 2 and 3, 3 and 4. And what we found is that 33% occurs between stations 1 and 2, 16% between 2 and 3, and 51% between 3 and 4. And you might be asking, why is this relevant? Well, what we considered is that if the train's going back and forth continuously throughout the day, we would expect it could randomly break down at any one point. But where is it likely to break down between two stations? And based on our total track length and the sections of track between stations, there's a 51% chance that it would break down between stations 3 and 4. So we went back and we asked ourselves, for each one of these design options, if the train broke down between stations 3 and 4, how many stations would be affected? How many stations would we not be able to provide access to our passengers? We went through each one of these. So single track, the average number of stations affected was 4. If there's only one train on that track, if that train breaks down, we don't have another train to provide access to the 4 stations. So all 4 would be affected. We would not be able to provide passengers to any of those stations. Whereas double track, if one train breaks down on one track, the other track is still fully operational. We can still move passengers back and forth. Now we might have to load those trains a little bit fuller, pack people in there a little bit more in order to move everyone along, but we'd still have access. We did the same thing for the options 3, 4, and 5. We had the average number of stations affected to be about 1.16 for 3 and 4, and then number 5 was 0.48. And then this is our final score tabulated. So we went through each of our 7 success criteria categories, gave it a total points, either out of 40 for the first one or out of 10 for the next ones. What we came up with was our highest ranking design option was the single track. Almost right behind it, and the 2 points down to 58 was option number 3. And our lowest ranking option was the double track, which had 51 total points. And again, this was out of 100. So what's our recommendation? After looking at all of our designs, looking at our success criteria, ultimately we would recommend going with option number 1. This is our recommendation to the city because it's easy to have the bicycle trail integration. Since it's only single track the entire way, there's still quite a bit of room, even in those narrow 30-foot wide parcels, to integrate that bike trail. It still meets our 30-year demand. All of these design options met our 30-year demand. We have low construction costs and low maintenance costs associated with design option number 1. And there's still the opportunity for expansion. So if we put in one track now, and later on our ridership increases above our expected values, we would still have the potential to add sidings at Park Plaza, or we even put double track the entire way down. That's just something that would want to be considered now when we design it, so we could leave that open for the potential expansion later on.